OpenFest 2024. Back to the source.
Lecture, which is about OpenVPN DCO on FreeBSD, and it will be presented to you by Kristof Provost. Please applause for him.
Thank you very much. Welcome, everyone. Quick bit of context. I'm a FreeBSD source committer, so yes, this is another FreeBSD talk. One of the things I focus on in FreeBSD is the PF firewall. This is not a PF talk, but I might sneak some PF references in there somewhere anyway, because I can't help myself. I spend most of my time contracting for Netgate. The reason that you see their logo here is because they sponsored the work to write a DCO driver for FreeBSD. We'll go into what is involved in that. For those of you who don't know, Netgate is a firewall appliance. Well, they sell firewall appliances and software. You may have heard of pfSense. They sell the commercial pfSense Plus product. Also Tensor, which is another firewall product, which is also very shiny. It's a vector packet-based processing for extremely fast routing and firewalling. It's very shiny. Enough about that. They're very nice, but we're going to talk about OpenVPN now. So first thing, what is OpenVPN? It's VPN. It's a bit of VPN software, which I'm sure you could have guessed. It was originally developed by James Yonan, original release in 2001. So this is a fairly old bit of software, which for those of you familiar with software, you know that that means it has all of the features. You can run it in peer-to-peer mode, you can do client-server setups, it has multiple different ways to authenticate, pre-shared keys, certificates, username, password. It runs on all common operating systems like FreeBSD, OpenBSD, DragonflyBSD. Also runs on some lesser-known operating systems like Windows and Linux and macOS, but nobody cares about those. The reason that I'm here is to talk about a problem, of course. I've just told you how nice OpenVPN is, and it is, but there is a problem. The problem is actually quite simple. It's slow. I mean, it works just fine for most VPN applications, of course, but once you start talking about modern networks, 10 gigabits, 40 gigabits, 100 gigabits, fast networks, it is very slow. Why is it slow? It's slow because it runs in user space. Well, that's part of the story. You can do very fast networking in user space as well, but that's a completely different talk. Let's not get into that now. The reason that it's slow is fundamentally this. You run OpenVPN in user space because it's a user space application. You run an application, say a web browser or wget or an FTP server, any sort of application runs in user space. It wants to transmit a packet that has to go over the VPN. So it does a send call, a write system call, the usual things that you do when you transmit data over the network. That data gets copied into the kernel. The kernel hands that over to the network stack. The network stack makes routing decisions, eventually decides that, oh, this has to be routed through the OpenVPN tunnel, which means it goes out over an IFTUN interface. This IFTUN interface then copies that data back into user space so that OpenVPN can encrypt the packet, can do all of the magic that it needs to do to provide VPN functionality, and then it will copy this data back into the kernel so that the kernel can route it out onto the internet or whatever network that you happen to be connected to. So you copy from your application into the kernel, back into user space, back into the kernel before it finally goes out. This back and forth trip, you're doing a lot of memory copy operations that you don't strictly need to do. You're also taking latency hits from switching between kernel space and user space, and this makes it slow. There are a bunch of reasons why the IFTUN interface is slow as well, but again, that's a topic for a different conversation. So how do we solve this? We solve this with DCO. It stands for data channel offload. The idea being that we move the data channel. So your actual data packets, your network payload that goes over the virtual private network, we move all of that into the kernel so that we skip the unneeded copying between kernel and user space. In FreeBSD, the driver that does this is called OVPN, for interface for OpenVPN, hence the title of this talk. That is one advantage. Another advantage is that you get to make use of hardware accelerators, hardware cryptographic accelerators. So there's a bunch of hardware out there. One of the examples right now is Intel's Q80 or Quick Assist that do encryption algorithms. So your typical AES or even ChaCha, depending on the hardware that you have, can do this in hardware, and they can do it much faster than your CPU can do it. The problem with those accelerators is they need drivers. Those drivers live in the kernel. So if you want to make use of a hardware accelerator from user space, you're stuck with the original problem that we had. You have to copy your data from user space into the kernel. The kernel can then hand it over to the hardware accelerator, which will do its thing, give it back to the kernel, which will copy it back into user space. And by then it would have been faster for user space to just do the cryptographic operations on the CPU directly. There's one exception here, which is AES-NI, stands for AES Native Instructions. It's basically an instruction set extension from Intel, although also available on other CPUs, that make it faster to run cryptographic operations, which is something that you do get to use in user space. We'll come back to this when I show you actual numbers. I promise there are numbers at the end of this. I'm not just going to say how awesome this is without proving it. Anyway, we end up with a DCO structure where we still have an application running in user space, so your web browser, your FTP server, whatever. It wants to transmit data. It will copy it into the kernel. The kernel will make a routing decision, eventually decides that the packet needs to go out over the OVPN 0 interface. But this time, rather than giving this packet back to user space so that OpenVPN can do all of the cryptographic operations, the kernel itself, the IFO-VPN driver, will perform the cryptographic operations. It will encrypt the packet. It will then make a routing decision, or rather, it will make a routing decision and then encrypt the packet. Come back to this. And then hand the encrypted packet over to the network stack, still within the kernel, which will then route it out, presumably over to the internet. Note that we still have an OpenVPN application running in user space. The kernel bits of this really only implement the simple things, that is, taking a packet, figuring out where it has to go, encrypting it, and sending it off, and vice versa when you're receiving packets, of course. All of the complicated bits, the policy, the initial authentication, dealing with the pre-shared keys or the public-private keys, all of that is still done in user space by the OpenVPN daemon itself. Hence also the ioctl interface, which is a communication between user space and the kernel to coordinate all of this. The end result of this, having moved the data channel into the kernel, makes things much faster. Because we live in a fallen universe, you can't have nice things without having some downsides as well. In this case, the downsides are not so much downsides as they are the OpenVPN project taking an opportunity to get rid of a lot of historical legacy features that they kind of don't want to deal with anymore. As I said initially, this project is more than 20 years old, so you pick up a couple of things along the way. One of the decisions they made is that they will only support AES GCM or ChaCha20 for encryption algorithms. This is fine. These are the only algorithms you want to use anyway. They've also removed stuff like compression support, fragmentation support, layer 2 support. So if you're using DCO, you must route. You can't transmit Ethernet packets over it. You can only do subnet topologies. You can no longer do traffic shaping within OpenVPN. This isn't actually so much of a loss because you get a specific network interface for OpenVPN. You can use whatever traffic shaping your kernel offers to still do traffic shaping, the way that you would do traffic shaping for any other traffic. So that's fine. As I said, the OpenVPN project used this as an opportunity for a clean break. It means that if you want to use DCO, you have to have an OpenVPN client of 2.4 or greater. I will point out here that DCO is not a protocol change, it's an implementation change. So it is perfectly possible to have a server that's using DCO and a client to not know about DCO at all, or vice versa. That will work transparently, that's all just fine. The reason for these limitations, as I said, get rid of some historical legacy stuff, but also for simplification of the implementation. To give you an idea, the FreeBSD driver is about 2,600 lines of code. Last time I checked, the Linux driver was about 4,500 lines of code. This is, some amount of code, but it is not an extremely large piece of code. And whenever you're dealing with security code, it's nice for there to be less code, because less code means less bugs, ideally. Some considerations, so I'll go into some topics, some issues that I ran into while doing this implementation, some things that you may not have thought about along the way. The first one of these is UDP versus TCP. Typically, you want to run VPN tunnels over UDP, because otherwise you can run into issues where you have multiple layers of retransmissions and it can kill your performance. The assumption is always that your layer 3 is unreliable. VPN provides layer 3 transit. It's fine for it to be unreliable, for packets to get lost along the way. OpenVPN does support running over TCP. The reason that they support this is because firewalls. Some networks, be they business networks or hotel networks, whatever, will drop UDP to ports that they don't know about. They will do strange things. Networks are just terrible. Firewalls are even worse. Ask me how I know. OpenVPN decided that they needed to support TCP. The FreeBSD implementation, we decided for simplicity's sake, we're only going to do UDP. Partly because we didn't really care about TCP. Basically, everyone runs OpenVPN over UDP. Also because it would have made the implementation a lot more complicated. There is an entry point in the kernel, we'll get into that later, where you can set a tunneling function. We have that for UDP, we don't have it for TCP. The OpenVPN people who implemented the Linux driver for this did add TCP support. I spoke to this person at an OpenVPN hackathon event, and they said that, if I had known going into this how much of a pain it was going to be, I might not have done it at all. You had a good point in just not doing it at all. They've got it now. I don't state categorically that we will never implement it in FreeBSD. But this code has been in use for a while, and I've not heard anyone complain that, oh, it doesn't work with TCP. It doesn't, so if you absolutely have to have it, talk to us, maybe we can do something. Second consideration is multiplexing. So it's data channel offload. We only offload the data that we transmit over the VPN. But there's other messages that get passed between an OpenVPN server and an OpenVPN client. Control packets, authentication packets, stuff like, hey, isn't it about time that we changed our key? Or stuff like the server saying, hey, I'm going to go away now, you should tear this tunnel down. That is not data, that does not go through the kernel, or does not end up being handled by the kernel, rather. Because of the way OpenVPN was developed as initially a user space application, everything wound up in the user space daemon. Everything is passed through a single socket, through a single connection, which isn't quite correct for UDP, but functionally it's a UDP connection. So these control packets arrive into the kernel, and the kernel needs to make a decision that, hey, this isn't the data packet, I don't know what to do with this. So it needs to be able to hand this packet back to user space so that user space can do whatever it needs to do with this packet. The way we've solved this is OpenVPN, when it starts a connection, will create a socket, a UDP socket in the FreeBSD case, and it will hand this socket over to the kernel when it says, when it's created an OpenVPN interface and it says, here's all of the configuration information that you need. By the way, here's the file descriptor that I'm using as a socket. The kernel will use this file descriptor attached to it with that tunneling function. But then when unknown packets arrive, so control packets, or possibly also packets for peers that the kernel doesn't yet know about, the kernel will hand this packet over back to user space. The way we've implemented this is actually fairly straightforward. I've mentioned this filter function. The packet so what happens is that the packet comes into the kernel. Well, a packet will come into your machine, it will be handled by your network card, the network card will raise an interrupt and go, hey, there's some data here. This gets handed off to the network stack. The network stack does all of its magic on it. We'll eventually find the socket layer, we'll find the socket that this packet belongs to, and then in our specific OpenVPN case, it will discover that, oh, there's a filter function, there's a UDP tunneling function rather, on this socket. It will hand the packet over to the tunneling function. The implementation of the tunneling function will look at the packet and go, oh wait, this is a control packet. I don't know what to do with this in the kernel. I will just tell the socket interface that, you know what, I changed my mind. I don't want this packet after all. And then the normal processing will continue as if there wasn't a tunneling function installed, which is a very long story to say that essentially the OpenVPN user space daemon will get woken up, its select loop will wake up and go, oh, hey, there's a packet here. I should read from this, this file descriptor from this socket and process the packet. This is actually one of the only changes I wound up having to make to the FreeBSD network stack. Everything else is just standard features that FreeBSD offers. Very early on in development, while the OpenVPN project was still trying to figure out how DCO would function, there was a slightly different flow. There was no way to just, or they did not consider just letting the packets continue on through to the socket. What they had was a special control interface via the ioctl interface that we'll talk about later, where the kernel would notify user space to say, hey, there's some information for you here. You should ask me to give you whatever packets I have pending, and they would get copied off through an ioctl interface. It's much simpler to just pretend that it arrived on the socket directly. Well, not pretend, it actually did arrive on the socket directly. We're talking about kernel code, so we are not going to get away from a quick discussion about locking. The primary reason to implement data channel offload in the kernel is to make stuff faster. We're talking about modern computers. How do they make stuff fast? They have multiple cores. You have multiple CPUs that can do work at the same time. We would like to take advantage of this. We would like to be able to process multiple packets at the same time. But we need to take care that our internal data structures do not become corrupted while we do this. We're all familiar, I'm sure, with the notion that if you have two cores doing stuff at the same time to the same data, you might end up with, with very unexpected results, and unexpected is very bad in the kernel. The way we've solved this in IFO-VPN is we've taken a relatively simplistic approach. What we have is an RM lock, which is a read-mostly lock, which is a read-write lock. So this is a lock where you can have multiple readers at the same time, but only ever one writer at the same time. RM locks are a FreeBSD notion. They are read-write locks, but they are optimized for the case where you have many more readers than writers. Just forget about that, it's a read-write lock. What we do is when packets come in or packets go out, we take the read lock. Because we know that we are not going to have to modify any of the internal data structures that tell us what the configuration is for this particular OpenVPN interface. Internal data for the driver is stuff like how many peers do I have, so how many clients are connected to the server, or vice versa. You know, it might only be one if you're the client connecting to a server. So peer information and also encryption keys, encryption and decryption keys. Those do not change as we process packets. So we take a read lock and we can have any number of cores doing this at the same time. We take a write lock when we make configuration changes. So we add or remove a peer, we change keys, things like that. Then we need a write lock. But those are extremely infrequent operations. You know, you might send 1 million packets before you change a key or before a client disconnects. So again, many more read operations than write operations. There are 2 exceptions to this. The first one is counters. So like many kernel subsystems, we maintain counters of how much work we've done. So for network interfaces, this is extremely common. We typically count, we've had this many packets come in, we've had this many packets go out, we've had this many bytes in, this many bytes out. There are a couple of error counters as well. So stuff like, you know, I tried to transmit this packet and I failed to allocate memory, so I just threw it away. Or stuff like, I received the packet and I tried to decrypt it, and it turned out that the authentication code that is included with the packet to prevent manipulation of the packet was incorrect. That might just be random corruption of the packet, or it might be an attack. These are the counters that we keep. The way we implement that is thanks to a counter framework that exists in the FreeBSD kernel. Again, based on the notion that we're going to be incrementing these counters far more often than we're going to be reading them. So to prevent corruption from having multiple cores update these counters at the same time, what we do is we just keep these counters per core. Every core has its own total for this is how many packets I've seen, this is how many bytes I've seen. And then whenever a user comes along and says, you know, I would like to know how many packets have gone through my OpenVPN interface, we go and look at the totals for every single core on the system, we add those numbers together, and then we can tell the user, in total, we've seen this many packets. That means that there is absolutely no locking required, there is no coordination required between CPUs, which is also an expensive thing to do. There's no coordination required until you get to the point where you're trying to read those counters. But again, we might transmit or receive 100,000 packets before the user goes and looks at how many packets have been there. The final exception is replay protection. So OpenVPN packets come with a sequence number, and it comes with a mechanism to make sure that sequence numbers don't get reused, essentially to prevent attackers from taking a packet that they've seen go by, an encrypted packet, they don't know what's in it, but they can take this packet and they can send it to the server again and again and again. The replay protection code remembers which packets it's seen before and goes, yeah, no, I've seen that one before, I'm going to throw it away. Unfortunately, there's no easy way to do this in such a way that is multi-core safe, because you need a single source of authority on, you know, these are the counters I've seen, these are the counters I've not seen. This is something where we need to take a mutex. So what we've done to make it fast is this is off by default. Now, if you're not cheating, you're not trying hard enough. Next consideration, the IOCTL interface or the IO control interface, however you want to pronounce it. This is the configuration interface between the kernel and user space. Sometimes, you know, user space needs to tell us, hey, I've set up a new server, here's the information that you need, here's the file descriptor, here's the port that we're listening on, all of those things. This needs to be transmitted between the kernel and user space. The classical approach for doing this is that you define a structure that says, you know, a struct OpenVPN key command or whatever that says, for this peer ID, this key, this algorithm, all of these things. You define the structure and you copy the structure into the kernel via the IOCTL system call. This works and this is simple. The downside of it is that if you ever decide that, you know what, I need an extra parameter in here, it becomes really painful because it's a structure of a known size and all of the fields are in known locations. If you add a field, suddenly you've broken compatibility between your kernel and your user space. So you end up having to do painful things like supporting multiple versions of the same call. It gets to be really painful. The way we've solved this in FreeBSD, for OpenVPN at least, is we have NV lists. NV lists are name value pair lists. So we define an abstract structure that says, okay, for name, peer ID, here's the value 2. For name, encryption algorithm, the value is 5, which we know happens to be AES GCM, for example. And then when we transmit this to the kernel, we make a binary representation of this data, send that to the kernel will unpack it again, and then go and look, oh, is there a key ID field in here? Yes, okay, here's the key ID value. Is there a key, an encryption key value? Yes, okay, let's copy that out. But if we add a field in user space that the kernel doesn't know about, or vice versa, they just never see them, and you can make your compatibility life much easier that way. Linux uses netlink for this. It would take us too far, but tackle me in the hall or something, and I will confess that netlink is a better solution to this problem. FreeBSD now also has netlink. Operative word there being now. While I was implementing the IFO-VPN driver, FreeBSD did not have netlink. If it had had netlink, I would hopefully have been smart enough to use netlink because it is genuinely better than the NVList approach. And it would have been compatible, or it would have been much more similar to the Linux way of doing things, and that makes life in user space easier. Unfortunately, it wasn't to be. So we still use NVLists. If somebody were really keen, I would be quite interested to pick up work from someone else because I don't want to do it. But if somebody wants to rewrite the interface to use netlink, I would be inclined to actually adopt that change. It would be a bit of a problem because we need to maintain compatibility between user space and kernel space, but eventually it would make life better. The next consideration is routing. Now you might think, but the kernel network stack has already made the routing decision. Surely you don't need to worry about routing anymore. And it turns out that actually we do. And this is because tunnels are not a broadcast domain. So imagine that we have a setup with an OpenVPN server running DCO, and it has 5 different clients. And a packet comes in and gets in and needs to go to one of these clients. Ordinarily, when you're on Ethernet, all you do is, okay, fine, we'll put the packet on the wire, and it'll go out, and it will turn up for at the correct peer, at the correct node, because it has the correct destination MAC address and everyone can see all of the packets, it will turn up for the correct client. This is not how tunnels work. We need to transmit the encapsulated packet with a destination IP address that corresponds to the correct peer. So we need to do an additional routing lookup. So the way this works is an additional routing lookup. The packet comes in, we look at the destination IP address. Is this the IP address of one of our peers? Yes, okay, fantastic. Then we know what peer to send it to. If it's not, we can do a route lookup. How do I get to this particular IP address? We do a route lookup, and hopefully the route lookup will tell us that, oh, actually the gateway for that particular route is this IP address, and this IP address is one of our peers, so we can do this lookup. For those of you reading along in the source code, this is OVPN route peer. I won't actually bore you with actual source code here, but that's where to find it. There is a special case for this. If we only have one peer, it says one client, one peer, the most common scenario where this is going to happen is you're an OpenVPN client, you're connected to a server, you only have one peer, the server. In that case, we don't bother with a route lookup. If we've decided that it needs to go through this particular OpenVPN tunnel, we just ship it off to the server, and the server can deal with it. Next consideration, key rotation. So I will confess I am not a cryptography expert, but I am told by people who are much smarter about this than I am, you can only use keys for a certain amount of time. After a while, be that a number of packets that you've encrypted, or an amount of data, or even a period of time, you want to change these keys. The actual key negotiation, so how the server and the clients agree on which encryption key they're going to be using, Is a problem that's handled in user space by the OpenVPN daemon? I don't know. This is for smarter people. User space makes this negotiation, but it needs to tell the kernel about this new key. Now, of course, the problem is if you change a key, both sides need to know about this at the same time, otherwise they're going to try to decrypt the packet with the wrong key, and they're going to get very disappointing results. So the way we approach this to make sure that we don't lose any data along the way is that we can have multiple keys be active at the same time. Multiple 2 keys. We can have a primary active key and a standby or an older key. So what we do is when it becomes time to negotiate a new key, user space negotiates the key, it will tell the kernel with the OVPN new key command, hey, there's a new key that you need to be aware about. This is the key ID, this is the key, here you go. Eventually, when on the receive side, packets will come in and we can look at the packet. It says, you know, this is the key that you need to use so we can receive these correctly. Or on the transmit side, we will use whichever key is the active key until user space decides that, hey, it's time to start using the new key. There's a swap key command, so we start using the new key. Because hopefully by that time our peer has installed the new key as well, it will be able to decrypt our packets and there is no traffic disruption along the way. After some time, user space will decide that it's done with the old key and it can say, hey, okay, delete the old key, we don't need it anymore. This is all driven by user space. There is also a mechanism for the kernel to say to user space, essentially send a notification to go, hey, it's about time that you change this key. The use case for this is essentially to prevent sequence number reuse. This is also for boring cryptography reasons that I'm not going to pretend to understand, but we can only use any given sequence number once. If we reuse them, it becomes a cryptographic risk. But user space doesn't know which sequence numbers we've gotten to because that's all handled by the kernel. So the kernel keeps an eye on the sequence numbers that it uses. Once it gets to a sufficiently high sequence number where it becomes time to negotiate new keys, but before it's actually too late, it will send a notification to user space with, hey, it's about time that you start your key negotiation, and then we do this whole key rotation dance. Final point I wanted to talk about is VNet. For those of you who were in the previous talk, Igor gave a good overview. For those of you who were not, think of VNets as Linux network namespaces. This is not a feature that was required for the use case that Netgate had in mind, but I added it anyway because it is extremely useful to test. It means that we can stand up jails, VNet jails on a FreeBSD machine and make them speak OpenVPN to each other as if they were different machines on different networks. It makes testing so much easier. For those of you who happen to have a FreeBSD machine around, users tests sysnet IFOVPN is where those tests live. If you didn't catch Igor's talk, I also did a talk about automated firewall testing, which goes into detail about how all of this VNet stuff works. That was actually presented at OpenFest back in 2020. Now, I've bored you enough with all of the implementation details. You're all here to see numbers, so let's take a look at some numbers. These were tested on a Netgate 4100. It's a firewall appliance. It comes with an Intel Atom C3338R CPU, which has QAT, so that's Intel's cryptographic offload technology. Quick assist technology is what they call it. It's a 2-core 1.8 gigahertz AMD 64 machine. So if we look at numbers, the original IF-ton is the old style, we do everything in user space. On this particular machine, we see a little bit over 200 megabits doing that. Now, the next thing we compare to is DCO in pure software mode. That is data channel offload, but without using any cryptographic acceleration at all, not even including AES-NI. So it's actually kind of an unfair comparison, because the user space implementation does use AES-NI. So we're comparing an accelerated user space to a non-accelerated DCO, and DCO is still faster. Not much, but it is faster. If we do a fair comparison, where DCO also uses AES-NI, we see that it is more than 3 times faster than the user space approach. If we do, well, I would still consider it a fair comparison. It's not my fault that user space can't reasonably use QAT. If we use the Intel's Quick Assist, we get more than a gigabit. So we're more than 5 times faster than the user space approach, which is very nice, both for, to say that, this DCO effort was worth doing. It also goes to show that Intel's Quick Assist is faster than Intel's AES-NI, which is good for Intel because they're trying to sell you more hardware, and they wouldn't sell a lot of hardware if it wasn't any faster than the hardware you already have. My own local testing also showed about a 3x performance improvement, and that is the whole point of DCO, is it's faster. And it is fortunately faster. Now that I've hopefully convinced you that you want this, how can you get this? You need OpenVPN 2.6.0, which should be easy because that was released early last year. You need FreeBSD 14.0, except don't run 14.0 because 14.1 is out. Keep an eye out because 14.2 is going to come out soon. They also have, that will also have IFO VPN included with it. You can also get this on Linux and Windows, but why would you do this? You just want to run FreeBSD, clearly. You can also get it on pfSense Plus, starting from version 22.05, which was released in 2022. It is, of course, also available in more recent pfSense Plus versions, because, if I'm remembering correctly, the latest pfSense Plus version is 24.03, with 24.11 coming out hopefully later this month. There's a little bit of future work that I'm planning to do, hoping to do, but I'm kind of stuck waiting for the OpenVPN project. They are looking at making some protocol changes. They're going to have a longer ID field, a sequence number field. They're going to move where the AEAD tag lives. AEAD is the authentication tag. So that's the bit of data that you use to make sure that nobody messed with your packet. They're going to move that to the end of the packet. And that sounds like something that won't matter. And for software implementations, it doesn't. But it turns out that when you try to implement something like this in hardware, it is much, much easier to do that if you can put the authentication tag at the end, because it means that your hardware can do encryption and it can already start sending bytes of the packets through to the next stage in the hardware pipe before it needs to deal with the authentication tag. So it can put the authentication tag in there once it's done processing it, rather than having to process and buffer the entire packet, put the authentication tag at the front, and then flush the buffer back out. It is basically a hardware optimization. Also with support for multiple key generations, they are working to standardize this new protocol version. That's not done yet, so clearly until the protocol is standardized, we can't update the implementation to match the new protocol version. All of this is work to make it work well with very, very fast hardware. 10 gigabits, 40 gigabits, 100 gigabits, because, it's the modern world. We all want our extremely high definition cat videos. I believe I've covered everything, so all that remains for me is to thank you very much for your attention. And to say that if you have any questions, you can find me here. You can contact me via email or Mastodon. I think we have a little bit of time left for questions.
Yeah, so if any of you has some questions, there's a microphone in the center. You could stand up and use it to ask the question, please.
Or you can find me at any time during the conference as well. Going once, going twice. Then I think the only thing I still owe you is the feedback form. So if you're unhappy with this talk, talk to the organizers. If you're very happy with this talk, also talk to the organizers. You should definitely thank the organizers for running a fantastic conference.